Hello everyone. This video is about the simulation of single-phase full converter. So for this simulation, we are going to use the MATLAB. In the MATLAB, open the Simulink. Then we have to create the blank model. For single-phase fully controlled converter, we need a AC source. So let us choose AC voltage source. Then we need 4 thyristors. Let us rotate the thyristor using Control R. Then let us name the device as T1 here. Since we need 4 devices, right click on this device and drag to get the second device. Again, right click and get the another device and then take the fourth device. Now all these devices should be arranged in the bridge fashion. So let us connect all the devices to form the bridge-like structure. So we have connected all the 4 devices in the bridge fashion. Now let us take the load as RL load. So type RL. So we will be having many branches. Let us choose the RLC branch. Then let us rotate this using Control R. Then we need only R and L. So right click on the RLC branch and choose only RL. Let us take the value of resistance to be 10. And let us use the same default value for the inductance. Now we are going to connect the load across this bridge and we will connect the AC voltage source to the bridge. Now we will be setting the amplitude as 200 and let us take the frequency as 50 for the AC voltage source. And we need to give the gate pulses for 4 thyristors. And for giving gate pulse, let us choose pulse generator. T1 and T2 will be conducting at the same time. Similarly, T3 and T4 will be conducting at the same time. So we need the common pulse to be given to T1 and T2 and the common pulse that is given to T3 and T4. So let us take 2 pulse generators. So right click on this pulse generator and we'll get one more pulse generator. And for giving the gate pulses, let us click on the pulse generator and let us take the amplitude as 5. And time period is nothing but 1 divided by the frequency of the AC voltage source, which is 1 by 50. And let us use the default pulse width. And for finding out the phase delay, let us take initially 30-degree angle. Let us take the firing angle to be 30. So 30 divided by 360 used for 1 cycle into 0.02. That is period. So that is the phase delay for the first set of devices. So let me connect this pulse chain data to the gate terminals of T1 and T2. Similarly, for next pulse chain data, we will take the amplitude as 5, period as again 1 divided by 50. Phase delay will be, already we have given 30° as phase delay for first pair of devices. So this will be 30 plus 180, so 210 divided by 360 into 0.02. And we will connect this gate pulse to other pair of devices. And in order to check the waveforms, we should use voltage measurement and current measurement. In order to see the output voltage and output current waveform, we need to use voltage measurement and current measurement. Let us connect the voltage measurement across the load and current measurement in series with the load. And to see the waveforms, you need to use scope. And since we have to see the two waveforms, current and the voltage waveforms, let us say the number of inputs is 2, so that we can see two waveforms in the scope. So we have to connect the current and the voltage measurement blocks to the scope. Then we will change the start time as, since the time period of the AC voltage source is 0.02, that is 1 divided by 50. We will view the four full cycle. For that, I'm going to give the stop time as 0.08. Now, in order to run this system, we need to use power GUI. Then only the model will run. So let us choose the power GUI block from the Simulink, and we will keep it in the system. Now we will run this simulation. So the simulation is over. To see the waveforms, you can click on this one. And so here we are getting the waveforms. In order to see the waveform as a separate windows, in separate windows, we can choose this one view option, and we can click on this layout, and we select these two bars to see the waveforms in the separate windows. So this is our waveform. The first waveform is the current waveform, and the second waveform is the voltage waveform. And we will change the inductance value. Here you can notice that the current waveform is discontinuous. This is the waveform for discontinuous conduction mode of operation. And since the load is RL load, we could able to see the negative going output voltage waveform, which is slightly going negative side. If we increase the inductance value, we can see the waveform, negative going waveform. So I'm changing the inductance value to 10 millihenry. Now let us rerun this one. So here we could see the negative going waveform, which is going in the negative side. So this is RL load. Single phase full converter can be operated as a two-quadrant converter, wherein the output voltage can be positive as well as negative. So we are getting the positive side voltage and the negative side voltage. Also, with this 10 millihenry, we are again getting the discontinuous conduction mode. If we increase the inductance values to still more, then we can achieve the continuous mode of conduction. So I have changed the inductance value to 50 millihenry. Now again, we will run this one. So here we are able to get the continuous conduction mode of operation where the current is of continuous waveform. And again, the output voltage waveform, we can see that the negative going waveform, negative going side, it is plotted here. So this is the rectification mode of operation since we have chosen the firing angle as 30 degree, which is less than 90 degree.